All right, so thank you for joining today. And I would like to thank also the Car Hacking Village for giving me the opportunity to give this talk, which is going to be about the kind of attacks that you can do on tire pressure monitoring systems. My name is Yago Lizarribar, and I'd like to introduce myself a bit before we dive deep. I'm a researcher in Switzerland, doing sort of work in the intersection between cybersecurity and artificial intelligence now. So like machine learning, deep learning, and these kind of models apply to cybersecurity. I do a lot of work as well in spectrum sensing networks, and I did in the past, long time ago, some work in autonomous vehicles. But this work I'm presenting today, it's a bit the intersection between spectrum sensing networks and cybersecurity. And before we dive deep, I'd like to also sort of summarize what we're going to talk about. The main part of this talk is the tire pressure monitoring systems, which are systems that are designed to increase vehicle safety because they are in charge of measuring what's the pressure of the wheels of a car. And being the wheel, the component that it's in contact with the road of the car, it's one of the most safety critical components, right? So knowing what's the pressure of each of the wheels of a car, it's really safety critical. They have been mandatory in the US and Europe for more than a decade, I think since 2007 in the US and since 2010 in Europe. So for a long time, these systems have been in place. And at the same time, cars have complex software stacks, and cyber attacks are very common. That's why the Car Hacking Village is part of DEF CON as well, right? So cyber attacks is very common in cars. For example, Europe now, since July 2022, requires that cars, all manufactured cars, provide a cybersecurity certificate that can defend the cars or the car owners from attacks that can reveal their identity, their location, and so on, right? And TPMS is not included in this. When we talk about TPMS, we have to make a distinction because there's a few families, and we're only going to talk about one in particular. The first one is indirect TPMS, which uses the sensors that already exist on the wheels, and based on the rotation of the wheel and many other geometry parameters of the car, they can estimate the pressure. Because pressure is a proxy of other parameters of the car, this is less accurate, and it's favored by Volkswagen Group, I'd say there, GM, and plenty of other, right? Then we have direct TPMS, which is these are sensors that are directly inserted into the wheel, and they measure pressure and temperature of the wheel directly, right? So these ones are usually more accurate because they're measuring the pressure of the wheel directly. These are favored by Toyota, by Ford, and original equipment manufacturers are usually using these sensors. And then we have another family that is more popular within Tesla and some specific manufacturers like Pirelli, which are Bluetooth-based, but yeah, Bluetooth also comes with some problems as well. In particular, in this talk, we're talking about direct TPMS. So from now on, when I mean TPMS, I'm meaning direct TPMS, right? So these are the sensors that are inserted in the wheel. So if you guys have a Toyota, Ford, Renault, Honda, perhaps, you guys can check today on your cars and see whether you can see it or not. But usually it's on the inflation rim where you can find the TPMS sensor. And I'd like to offer a very brief direct TPMS primer before, again, we jump in. So the inside of a TPMS sensor is a battery-powered device. Usually, they transmit the information wirelessly to the ECU, and the protocols are usually proprietary. There's no open source protocol or anything. So each manufacturer has its own way of sending the information. The problem is that even though they're proprietary, they don't have any sort of encryption or authentication or anything, which means that they're very easily reversible. And now there's a myriad of libraries, there's a million of attempts, and one of the most prominent ones is RTL433, which basically does most of the work for us, right? The modulations that they use are really nothing extraordinary, so simple amplitude or frequency shift keying. In Europe, we use 433 megahertz. In the US, probably it's 915. If someone can correct me, please feel free. But yeah, it's usually ISM band transmissions. Inside a TPMS sensor, we have different components. What we have is, of course, the MCU that takes care of the motion sensor, the pressure sensor, and the temperature sensor. So usually, or in theory, TPMS sensors should only transmit information when the car is moving. So, and then when the car is moving, they transmit every 60 seconds, right? So it depends on the manufacturer. When they're parked, they should not transmit. And one component that it's usually overlooked on TPMS sensors, of course, you have the RF chain, the transmit part, so when they send the information wirelessly to the ECU. But there's a receive component that waits for a single signal at 125 kilohertz, and this signal usually activates the whole transmit pipeline so that it sends immediately pressure information, right? And for example, nowadays with this kind of devices, well, they contain here a transmitter at 125 kilohertz that can activate any sensor that you want, so long as you are close enough to the wheel of the car, right? And then a typical TPMS frame contains temperature information, pressure information, but also a sensor ID, which is 32 bits. And so that means there's like around 4 billion unique IDs, right? Perhaps why this is dangerous is because all this information is sent in clear with no encryption or anything, right? So the only safety measure here is that the modulations are proprietary. As I've said before, this is really not an obstacle to anyone, right? With enough knowledge. That's why even 15 years ago, there were some papers. In 2018, there was a talk here at DEF CON about TPMS, right? So there were already people thinking that it's possible to to do both sides of the attack. So one is the passive monitoring, and the other is the active attacking, right? So what happened in the last 15 years, since 2010, for example, until today, with regards to direct TPMS hardware, is that nothing changed. It's just that SDR receivers and hardware in general got much better, right? So now it's even more feasible to set up attacks in any form or any way, right? So this talk is divided into the two types of attacks that you can do on TPMS system. One is the passive monitoring, which we'll now describe, and then the active attacking. So for the passive monitoring, we started this a few years ago, of course. We got the permission so all the data that we will show, it's from participants that participate in our studies, so we have permission, right? But there was an IT director who had a Toyota, and doing unrelated measurements, what we could see is that we could track his TPMS tires. Ergo, we could track his car over the time, right? And after some time, we could start learning his absences, when he was out, when he was coming, et cetera, right? So we asked ourselves, is it actually feasible to track cars or to track DTPMS and consequentially track cars? And what patterns can we learn, right? So here we have a bit like the distribution of how many TPMS messages we could see per week and also by the hour of the day, right? So we can start noticing some patterns, right? So for example, this was very old measurements, right? So this was one of the COVID lockdowns we had back in Spain. We can also see when he was on holidays. Of course, we can easily determine what's the working hours of this person, right? So there's a lot of things that we can learn almost without noticing or without even trying, right? So what we did is we took 12 participants, or we did a small study, and then we tried to set up a car tracking infrastructure for these particular users. But there's nothing really blocking anyone from building a big setup to track any cars that use direct TPMS, right? So what do you need to build such an infrastructure? So what you need is hardware, of course. That is around $100, which contains an RTL SDR and a 433 megahertz antenna. In US, perhaps a different frequency antenna, but the same principle applies. Single board computing, like a Raspberry Pi, internet connectivity and power, right? So in Spain, you can get this for $100, perhaps in the US a bit more, but it's around the price tag, right? The software on the device only needs to be the RTL 433. What we have is also some custom models to avoid any processing of unwanted data. And then the infrastructure is very simple. So there's plenty of open source components that are really readily available so that you can send this information to a database and basically start collecting data, right, of TPMS sensors. So yeah, in a few weeks' time, you can capture millions of unique IDs from nearby roads. We'll show later how far even, right? But the infrastructure looks very simple, right? So you have cars transmitting direct TPMS messages, which are intended or which are directed to the ECU, but because there's no control on this, anyone listening can also receive these messages, right? So then the decoded messages via any software that exists already can be parsed by InfluxDB or any time series database that exists. You can have your pretty Grafana dashboards. You can download this data and apply your pretty nice analysis algorithms. You can do plenty of nasty stuff, right? That's some risks. One thing that we notice, of course, is that each car has 4 wheels, right? So a question that arises is how correlated are the measure or the transmissions of its TPMS sensor with each other, right? So the 4 TPMS sensors of a car, let's talk about cars. Do they transmit at similar times? Is it difficult to correlate? Of course, because if you only use one ID to track a car, you're missing a lot of information compared to when you track all cars at the same time, right? So you're gaining quite a big advantage. There's several methods that are in the literature we can use and apply to this particular problem, which are, of course, the cross correlation of the time series, the Jacquard index. So I won't get too much into the details, of course. We designed something based on the Jacquard index with a bit of a robust matching. And what we notice is that in the end, we can capture, if you see, we see groups of 4. So this time, this represents the IDs detected the number of times, right? So most of the time, IDs appear in these blocks of 4, which means that TPMS sensors tend to fire at similar times, right? So it's very easy to detect which sensors belong to the same car compared to other cars. There's also other tricks because manufacturers usually design for a particular car, when they program the bits or the ID of the TPMS sensor, they usually use the IDs are equal to the first 26 bits out of 32, so only the last ones are different, right? So it's also a good way to notice whether they belong to the same car or not. But then we can after we do the setup, after we analyze how the different TPMS sensors of the same car correlate, we can start analyzing long-term patterns, right? So what we saw here, so the black lines or the black dots mean at a particular day, at a particular hour, whether we saw a particular TPMS car or a particular car, right? So we are taking into account now the 4 TPMS IDs. So this is for a part-time student that was working with us. So what we see is that this person was usually coming from 8 to 1 p.m., right, to work. But we can start seeing some anomalous behaviors, right? So in this case, for example, we saw this guy coming even on a holiday, quite late at night. And actually, that was not that he passed by where we were, but he was on a road nearby and he was on a university course, and we just happened to capture him, right? We can actually manage as well to detect other anomalous behavior. So this person came on a holiday because he had quite a tight deadline working on. So yeah, this kind of stuff that we can easily learn without the knowledge of the car user or the car owner, right? So this is not something that you can control. This is information that is sent by the wheels and that you have no control. We also were very nice, so because we're getting the pressure sensor, so we warned the pressure of his front wheels was a bit low, so we were nice enough. This is a bit of a silly example, but there's a lot of information, but for which you have no control of, right? So that's the worrying part. There's plenty of other long-term patterns that we can learn. So on the left-hand side, we have like a full-time worker. This car in particular is sort of adheres to the standard design principle of a TPMS sensor, meaning that we can only get this car when it was coming or going, so meaning when the car was moving. If we look at of course, we can still see some anomalous things, like, for example, in the middle of the day, he went for lunch outside the building, so we can also detect that. We can detect a bit of so he came and left quite early, so these kind of anomalies we can also detect. In this case, for example, on the right-hand side, so we can detect full weeks where he was not coming, but also here, also the most interesting part is also that the car, even when it's parked, it's also transmitting, right? So not all sensors work the same. Also, when the car is parked, even when it's not necessary to know the pressure, we can still get a lot of information. And the last one, not because there's no interesting pattern, but because the way the data is being sent. This is the case for Toyotas, and this is for the Toyotas that we've seen in Europe that use a particular vendor, which is PMV. And what we see is that this transmit information or the pressure information with the ID every 15 minutes, no matter whether the car is parked or moving or doing anything, right? So what we found is probably Toyota is the chattiest brand of them all, or at least the manufacturer for Toyota is the chattiest brand of them all. And they also transmit with high transmit power, right? So we could detect, particularly we could detect Toyotas up to 200 meters or something. So that's quite far compared to other brands, which is a bit less. Now the question is, okay, so we're focusing mostly on parked cars or nearby cars, but what are the limits to this tracking infrastructure? So what happens when there's more cars, when they're moving fast, or when they're far, right? So we did an estimate, of course. We cannot test with that many cars, but we estimate that one single sensor can track in 30-second windows up to 200 cars with quite good reliability. One of the scary parts of tracking TPMS compared to using cameras or using other devices is that tracking TPMS, you don't need direct line of sight, so you don't need to be directly pointing at the road, so you can be hidden somewhere and basically capturing. So what we saw is that even in no line of sight, so when we have walls and when we have no direct line of sight of the road or anything, we can still capture TPMS messages up to 60 meters with very simple hardware again, right? So this is the scary part. And up to 50 kilometers per hour, which is 30 miles per hour, I think, you can still capture messages quite easily. So here what we had is a car doing laps around a neighborhood. And except for lap number 4, which where the sensor that we were using collapsed a bit, all other laps we could capture at least one TPMS ID, right, of the car, right? So it's really up to urban speeds, it's quite doable. I would say that for highway speeds, perhaps this is not feasible. So now when we move, it's okay. All right. So we move on from the passive monitoring to the active attacks, right? So because this channel, is this something causing this? Is the room? Okay. Okay, sorry. That's a bit distracting. But yeah, so the thing is that the TPMS channel is not authenticated and encrypted or anything, right? So we can monitor, but we can also spoof, right? And be a bit even nastier than before, right? So what we did, for example, is so we had a car that we could use that obviously uses the TPMS. The modulation of the Renault, again, it's not public anywhere, yet it's widely known. What we built is a signal spoofer, and then we extended it for a few more cars, and we are working on extending it and doing more tests, of course, so that to see how the car responds to different messages, right? So some of the characteristics that Renault uses, so it's true that it's easy, but each brand has its own quirks, but it's really a matter of documenting and storing everything, right? The frequency in Europe is 433 megahertz. The modulation is 2 FSK plus pulse width modulation. Then it uses Manchester encoding. The bit duration, so each bit lasts around 52 microseconds. And the main things you can obtain from this are some flags for the message, the ID that uses 3 bytes, the pressure and the temperature, and lastly, some battery voltage and some unknown parameters that related to how the tire is deflating, etc. Right? Here, the toolset is slightly more complex than for passive monitoring, but not much. So what you need now is an SDR with transmission capabilities. So usually we use the User P Mini, which is a bit pricier, but nowadays for $300 or even less, I think the Flipper Zero has transmit capabilities and it's cheaper than this. So yeah, pretty much, as I said before, in the last 15 years, TPMS technology didn't change. It's just that the SDRs became cheaper and more powerful, right? Which is kind of scary. But yeah, we can take the receive pipeline or the decoding pipeline, and then we can basically reverse it, and then we get our spoofer there, right? So for the case of Renault, when you decode, so you have the TPMS sensor that is transmitting the signal. We need an SDR with receive capabilities. We then modulate the 2FSK. We then modulate the pulse width modulation. We do a bit inversion, Manchester decoding, and suddenly we have our message, right? So work done. What do you need to transmit? The same, just reverse. There's literally nothing extra, nothing fancy, nothing special, right? And then you can transmit this signal to the ECU, and because there's no authentication or encryption, the ECU thinks it's just its own TPMS sensor, right? Just to show how these things look like, I'd like to, so for example, right? So we started with the 2FSK. So what we have on the top and the bottom is the 2 frequencies, right? So each frequency, when it jumps, it's a 1 or it's a 0, right? So we have here, we have a jump, it stays for the bit duration, so 52 microseconds, and then when it's a 0, it jumps to the other frequency, and when it's 1, it stays, right? What we get now, it's on time. We get this sort of these time-based lines, and basically we can divide in between the times where it's at frequency 1 and the times where it's at frequency 2, right? And then we can calculate what's the width spent at each of these frequencies. So in this case, we start with a 1, so we stay at a tuple of 1 at frequency 1 and 1 width at frequency 2, then one moment at frequency 1, and then 2 moments at frequency 2, etc., etc. Then we can go from the pulses that we have, we generate this tuple, and we generate a sequence of bits. So the frequency 1 represents a 1, the frequency 2 represents a 0. Simple as that. We invert the sequence. This is how Renault does it. many other manufacturers don't take BERT, so it's really manufacturer dependent. With the Manchester decoding, they want to be robust enough, I guess. We found a preamble, so yeah, it's good that many manufacturers include preambles so that we can detect easier, or we can sort of discard false positives. In the case for Reynolds, it's this starting value, and we get the final message. And the final message is, again, very easy to obtain the information from. So we start with the flags, we start with the pressure, the temperature, the IDs, of course, and the other parameters. And we get a nice CRC8 just to check whether we decoded it properly or not, which is very nice. And again, to transmit, we just reverse the flow. There's nothing else. There's really no magic to this. So then what we can do is we built a spoofer with these principles, and we started spoofing stuff, right, and detecting. So one of the biggest issues what we found is, of course, you can provoke this Reifenpanne. This is in German because we're in Switzerland, but it's basically faulty tire. This is also a really annoying noise. You get it all of a sudden, so it can be very scary. Of course, the tool that I presented here can also get spoofed. So long as it's easy that this tool exists, because so long as you can spoof this tool, you can spoof the car that you're trying to spoof, right? So there's a lot of infrastructure that you can use to really refine your spoofers. So to wrap up, what can we conclude, right? So DTPMS are actually quite vulnerable to all sorts of attacks, whether they are passive, whether they're active, whether you can mix them, right? So if you track a car over time and you can select specific locations where you want to inject a faulty message or a faulty pressure message to the car and then provoke that this person stops or anything, if you're a logistics company or you're tracking somewhere, right? So it's just because the channel is not encrypted or authenticated, you can be as nasty as you want. Given the status so SDRs are becoming cheaper, are becoming better, and the technology is not getting much better, right? Also, what we noticed, and again, we want to remark, is that passive monitoring is affecting some brands way more than others. So for example, what we saw is that Toyota, it's particularly bad in this case because they're transmitting every 15 minutes, no matter where the car is moving or not. Other brands like Renault or Hyundai, I really respect more the core design principles of this. So yeah, you're safe, right? And the question is there a solution to this? And the bad answer is that if you had a car with DTPMS, probably not right now. Because so the way the system is designed, the ECU expects the messages in clear text, right? So if you have a DTPMS car, there's nothing you can do. If you're thinking of buying and you're worried about this, then you might check whether your car is using DTPMS or not. Actually, yeah, so again, one thing that you can do is not everyone needs the accuracy of DTPMS. So I have indirect TPMS, and for me it's good enough, and I had tire deflations, etc. But again, it's not feasible for many cars that are running right now. There exist plenty of papers that had shown that it's possible to add encryption or to add different designs, but yeah, they mostly stay on the research. So there's really no one. I've never seen a car that has implemented any security measure for DTPMS, right? And because, yeah, open source, again, is very important for us. So we provide two repositories to replicate this research. So the one on the left is the TPMS analysis, so the tools that we use to analyze passive monitoring systems, and the TPMS tools, which are the sort of how to spoof and yeah, do all kinds of nasty stuff. And this should be all. How much time? Thank you. Oh, yeah, sorry.
Take question.
Yeah. You spoke about stability, an error or a low tire pressure. And maybe talk a little bit about the behavior you saw in Street Plus, but also the opposite, like deflate someone's tire and show that it's spoofing the tire is deflated.
That's perfectly fine. Yeah, absolutely.
Is it the power that you're looking at? Is what the ECU detects? Or is it the override?
I think my experience or my impression is it doesn't care. It's just a first come first serve. So if you're transmitting more often, then it will take more attention to what you're doing. Because what I did for the deflation part, I was moving the car, but it was basically transmitting every second. So you're basically overloading the ECU with low pressure messages. So the every minute, exactly, right? So I think it's first come, first serve.
And so what were you talking about the speeds? You said there was at 50K.
I'd say it's the highest we tested. So we're sure that up to 50 kph or kilometers per hour, we can decode TPM message easily. Perhaps it's even more. Like it depends how much time you travel, right, at 60 kph. So if you have good antennas and good hardware, you can increase the distance at which you detect the TPMS message, right? So
Does all DTPMS give temperature data?
I think most, because usually if you park, for example, your car in a cold location, you might trigger the system, right? So you need this temperature measurement to say, okay, it's because the temperature is low. So I would say.
A bunch of forms, they give you they give you pressure, but not temperature. But I want to know the temperature. So I'm wondering if I could use this to read the type.
Yeah.